Assalamu alaikum dear students. Today we are going to discuss Syllow's second theorem and a few of its consequences as well. We will try to elaborate this theorem with the help of examples and we will give its formal proof. Okay. I suggest to watch my last lecture, lecture number 10, group 3-2, for the understanding of double cosets representation of a group G. If you know about the double coset representation that we have discussed in detail in our last lecture, in lecture 10, then I think the proof of Syllow's second theorem would become so easy. We can easily prove this theorem. So what is that theorem? Any two Sylow P subgroups of a group G are conjugate to each other. You know, any two conjugate subgroups are in fact isomorphic to each other. So you can say also that any two Sylow P subgroups of a group G are isomorphic to each other, right? So suppose you take S3, and you know S3 has order 6. So with respect to Sylow first theorem, the order of S3 is 6, which is 2 into 3. Okay, by the first theorem, first Sylow theorem, you know that what is first Sylow theorem? Is that if a prime number P divides the order of a group G, then that group has a Sylow P subgroup, has at least one Sylow P subgroup. So it was sufficient to show that it has a Sylow P subgroup that would satisfy the condition of at least. Okay, you know the order of S3 is equal to 6, which is 2 into 3. So with respect to Sylow first theorem, you must have a Sylow 2 subgroup in S3, and you have a Sylow 3 subgroup in S3. So you know that what is S3? S3 is equal to E A square, then B A B, A square B. So these are the 6 elements. These are the 6 elements. We like to write as well in genetic form. A B such that A cube is equal to B square is equal to AB square is equal to E. This is the genetic form. So can you find the 2 subgroups and 3 subgroups of S3? You know that there you can see that H1, this is EB. Yes, it's a subgroup of S3. You see that B square is equal to E. So that's why EB must be a subgroup of S3. Similarly, you have another subgroup H2, that is EAB. Another subgroup H3, this is EA square B. If you know the order structure, so the order structure is, its order is 2, its order is 2, its order is 2, its order is 3, its order is 3, its order is 1. This is the order structure of S3. I think everybody can calculate by using these generators. From here you can see that B square is equal to E, so order of B is equal to 2. Similarly, we can show that order of AB or AB square, here AB square. AB square is equal to E, so order of AB is equal to 2. You can find the order of A square B. So for A square B, if I check A square B square, this is A square B into A square B. So this is in fact A square B A square B, and you know what is B A square? B A square is AB in S3. This is A square AB B. This is A cube B square E E. This is E. So look at, this is the least positive power for A square B, which is assigning the identity element. So order of A square B is 2 as well. So these are the 3 elements of order 2. That's why they must generate cyclic groups of order 2. So these are the two subgroups. So we have two subgroups in S3. So these are the two subgroups, two subgroups, two subgroups, and you have another subgroup which is a three subgroup. That was A square. So say this is your H4. It's a three subgroup. So S3 has two subgroups and one Sylow three subgroup, right? So you see that with respect to this theorem, first we are using the Sylow first theorem. Sylow first theorem says that if a prime P divides the order of a group G, then G must has at least one Sylow P subgroup, right? So that's why, since 2 was a divisor of 6 and it is a prime number, so that's why you have three Sylow P, two subgroups in S3. And 3 is also a divisor of 6, so that's why you have a Sylow 3 subgroup. But you know that this is the only subgroup which is a 3 subgroup in S3. Now you need to see that what is the relation between these three to each other is that any two Sylow P subgroups of a group G are conjugate to each other, are isomorphic to each other. Yes, you can see the isomorphism very easily, because AB is of order 2, B is of order 2, so there is no problem, just the difference of symbols in fact. So their structures are same and all are the cyclic group, and you know that C2, there is only one cyclic group of order 2. There is only one cyclic group, there is only one group of order P, that is CP, you know very well. So that's why there is no problem that you can easily prove that these are isomorphic to each other. Anyhow, you can see the conjugation relation as well, they are also conjugate to each other. We can establish with the help of very easy calculation. You can see that there must be some element in S3 for which you can see that H2, A inverse is in fact H1. You know what are the conjugate? If H is a subgroup, then A inverse is equal to K. If you can establish this relation for A belong to G, then we will say that K is conjugate to H, and conversely H is conjugate to K as well. So our second theorem says that any two Sylow P subgroups. So this means that a group G can have more than Sylow P subgroups. One thing is this, that a group G can have more than one Sylow P subgroups, but according to this theorem, they must be conjugate to each other. So let's try to identify whether these are conjugate to each other. Okay, we can see easily. So first is H1 is equal to EB if I multiply by AH A inverse, then what will happen? This is AE A inverse, AB A inverse, yes, and try to simplify this. This is E and this one is AB. What is A inverse? You know in S3, A inverse is A square. These two are the inverses of each other because both are of order 3. You know that the A and A inverse both have same order, and you have exactly two elements of order 3. That's why they are inverses to each other. So A inverse is equal to A square. And what is B? A square. E A and B A square. You know B A square is in fact AB. B A square is AB. So what is this? This is E A square B. Look at this. What is this? This one is H3. This one is H3. Right. So A inverse is H3. This means that H1. So H3 is conjugate to H1. Similarly, if you multiply instead of A, if you multiply by AB, what will happen? We see that. Remember these three subgroups, two subgroups. Okay, so my H1 was EB. If I multiply by AB H1 AB inverse, then what will happen? This is in fact AB AB inverse, then B AB B AB inverse. You see, this is the identity. And what is AB AB inverse? You know, AB inverse is B inverse A inverse. This is B A square, right? So this is AB and B. So AB inverse is equal to AB inverse. You know, AB square is equal to 2. So this implies AB inverse is equal to AB. That's why. So AB inverse is equal to AB. Also you can check like this. AB inverse is equal to B inverse, A inverse. You know, B inverse is B. This is A square, and B A square is equal to AB. Very easy. So this one is AB. This is A. B square is identity. So B square is identity. So you are getting A AB. So which is E A square B. Right. This is your H3. Yes. So H3 and H1 are conjugate to each other. Again, you are getting H3. You in this way you multiply H1 with the help with all other elements, right? If you multiply by A square, then what will happen? You can check. Now, if you multiply H1 by A square inverse, you know, this is A square, and you know what is A square inverse? A square inverse is in fact A. So this is in fact A square H1A. This is EA, then A square B A, and what is this? This is E, and A square BA is equal to A square. What is BA? This is A square B. So look, this is E A4. This one is A4B, and you know A cube is equal to identity. So this is equal to E AB. Look, this is H2. Yes, H2 is also conjugate to H1. You have seen that A square H1, A square inverse is in fact H2. So now we have a better understanding of the statement is that any two Sylow P subgroups of a group G are conjugate to each other. This means that you can have more than one Sylow P subgroup, but remember, corresponding to a fixed prime P, whatever the number of Sylow P subgroups, they must be conjugate to each other. I mean to say, from one Sylow P subgroup, you can always establish the second one by multiplying by pre and post multiplication with A and A inverse respectively. So now come to the proof of this theorem. Proof is so easy. If you know the idea of double coset representation, then we can easily prove this theorem. Okay. Now we will try to prove this theorem. Okay, proof is let G be a group of order n, let H be a Sylow P subgroup you take two Sylow P subgroup H and K. Let HK be two Sylow P subgroups of G with order of H is equal to P power alpha, which is also is equal to order of K as well. Okay, this is our theorem. We are taking two Sylow P subgroups, and you know that the order of Sylow P subgroup must be same, because if P power alpha divide order of G, then P power alpha plus 1 does not divide order of G. That's why you are saying that H is a Sylow P subgroup. So if you are taking another Sylow P subgroup of corresponding to same prime number P, then its order must be P power alpha as well. There is no ambiguity. There is no hesitation to write that order of H is equal to P power alpha, which is equal to order of K as well. Right? Okay. Let suppose index of H in G is equal to M, then by Lagrange theorem, then by order of G is equal to order of H into index of H in G, right? So you are getting n is equal to P power alpha m. Remember here P and m are relatively prime, right? Clearly here P and m are relatively prime. Okay, if they are not relatively prime, in the last lecture I have elaborated that the relation between a prime number and with any other number, either P and m are relatively prime or P is the divisor of m. If P and m are not relatively prime to each other, then P would divide m, so this implies m would be equal to some Pm1, and if you substitute here, you will get n is equal to P power alpha into Pm1, with P and m1 are relatively prime, so this implies P power alpha plus 1 would divide n, and this will indicate that H is not a Sylow P subgroup, because you have supposed that H is a Sylow P subgroup, so order of H is equal to P power alpha. This means that P power alpha is a divisor of the order of G, but P power alpha plus 1 and higher powers can never divide the order of G. So that's why by Lagrange theorem, whenever you write Lagrange theorem, n is equal to P power alpha m, and P and m must be relatively prime to each other. Means that P is not a divisor of m. Remember, this is your first condition, right? I am saying that if this is not the case, then of course P will divide m. This implies m must be equal to some Pm1, and after putting here, you will get P power alpha into Pm, means that P power alpha plus 1 m1. This means that P power alpha plus 1 divide order of G, a contradiction. That's why this is very important condition, that P and m are relatively prime. Okay, now consider the double coset representation of G modulo HK, and suppose there be R possible double coset representations modulo HK. Okay, this is our condition number 1. uh, assume that there are possible distinct double cosets of G modulo HK, then the set omega is equal to H A K, A belong to G, is the partition of G, right. This is very much clear. We have discussed in detail in our last lecture, in lecture number 10, that what do you mean by a double coset representation and how you can find double cosets and what is the relation of double cosets with G. You know that the collection of all possible distinct double cosets is in fact a partition of G. So this set, this is containing all possible double cosets. Mean to say that HA1, you are saying that here are, these are A1K, HA2K, and so on, HARK. So these are the possible double cosets modulo HK in this case. So then by inclusion exclusion principle, or you can use the word partition, since omega is a partition of G, so we must have order of G is equal to, or G is equal to union of I varies from 1 to R H A I K. If you take union over the entire set, entire partition, then you will get G. Then by inclusion exclusion principle, because HAIK intersection AJK is empty as well, that's why. So by inclusion exclusion principle, we have this principle says that if G is the union of some disjoint sets, then order of G is in fact the sum of their orders, right? So order of G must be equal to summation order of H A I K, I varies from 1 to R. And you know that its order is, last time we have established its order as well, because you know that you have established order of HK. This is in fact was order of HEK, and also you have established order of HK as well. So both have the same order. We have established order of H into order of K over order of H intersection AK A inverse, right? So this becomes this is equal to n summation I varies from 1 to R order of H into order of K over order of H intersection A I K A I inverse. Let's see the order. You know that order of H is a Sylow P subgroup and K is a Sylow P subgroup. So order of H and order of K both are P per alpha. And what is the order of this? Its order is Qi, you know. Its order is Qi. this is equal to p power alpha into p power alpha over qi, I is from 1 to r, where qi is equal to order of h intersection ai k ai inverse we have established in last theorem. Okay, so this is n. Since summation is over I, that's why this p alpha is free from this summation. So that's why you can keep this out of summation as well, right? So what is this? So this implies n over p power alpha, which is equal to summation I will from 1 to r. This is p power alpha over qi. Right, we can write this is, then look at equation number 1 by Lagrange theorem. You know that you have written that n is equal to order of h into index of h in G, and you have supposed that order of h, this is n, and this one is p power alpha, and this was m. So n by p power alpha is in fact m, and remember p and m are relatively prime. This was your equation number 1. So from here n by p power alpha is equal to m. So this implies that m is equal to summation I is from 1 to r p power alpha by qi, using equation 1. You are at this step. Okay, from here we can easily write this is in fact you're writing m is equal to p power alpha by q1 plus p power alpha by q2 plus 1 plus p power alpha by qr, because there are possible double quotient representations modulo hk. Okay, now what is q1? Q1 is in fact, look at here to understand. The order of Q1 is in fact order of H intersection A1K A1 inverse. Now look, A1K A1 inverse. The order of A1K A1 inverse is in fact the order of H. So this is it's a the order of k, and this is equal to order of p power alpha. Look at here. Since A1k A1 inverse is conjugate to k, there is no problem, and k is a Sylow p subgroup. So that's why A1k A1 inverse, this is also a Sylow p subgroup. Look at here, one is k and one is A1 k A1 inverse. Look at here, k is a Sylow p subgroup, so A1 k A1 inverse, of course this also must be a Sylow p subgroup, right? Because their order are same, so its order is also some p power alpha type. That's why. So every q1 is divisible by some power of p. Okay. So there is a possibility that corresponding to some AIs, this could be equal to p power alpha as well, because some A1k A1 inverse, this is in fact a conjugate subgroup of k as well and conjugate to k as well. So its order is in fact the order of k. You know that order of A1k A1 inverse is in fact order of k, and k is a Sylow p subgroup. So we will discuss in general. Rather we fixing the idea. You like here you can understand that H is a Sylow P subgroup, and this is also a group whose order is some power of p. This is true. If you are not sure that whether this is a Sylow P subgroup or not, because this is a conjugate subgroup, so here we should not use the word Sylow P subgroup, because we want to show that yes, it is a Sylow P subgroup, and this is conjugate to K. So, but one thing is very much clear, that its order must be some power of p, right? This is also a p group, this is also a p group, so their intersection must be a p group. That's why Q1 must be some power of p, right? So we are writing this thing is that since Qi is for I is equal to 1, 2, 3, so on up to R, are the orders of P groups. This thing is very much clear that A1K, A1 inverse, you know, order of A1K, A1 inverse is in fact order of K. This clearly shows that A1K, A1 inverse is a P group. H is a P group. So their intersection must be a P group. That's why this Q1 must be divisible some prime number P, right? The same prime P, because for which P power alpha is the order of H, okay? So since Qi is for I varies from 1 to 3 to R are the orders of a P group, so that each term, on right hand side must be either multiple of P or 1. Why I am saying that it could be 1? That there is a chance that its order is in fact there is a chance that for some Qi order is P power alpha. There is a chance because both are the P groups. So if I am saying that the order of Qi is P power R, then of course P power R is dividing P power alpha. So that's why there is a chance that R could be alpha. There is a chance. And you know that the divisor of P power alpha, what are the divisor of P power alpha? The divisor of P power alpha 1, P square and so on, P power alpha. So the order of Qi must be some power of P, and since it's a divisor of P power alpha, there is a possibility that sum of the order of this group is P power alpha. So there is a chance that sum of the Pi, this is also important, because if each term is a multiple of P, then the right side would be divisible by P. So because the left side, but left side is not divisible by P. So there must be some term which is equal to 1. So there must be some Qi for which order of Qi is equal to P power alpha. Okay, now I am writing this result. Okay, here I am writing with the help of P groups. Since Qi is for I varies from 1 to R are the orders of P group, so the each term on right hand side must be either multiple of P or 1. Say you have P 3 and here order P square, this could be P, okay, and say here you have P 4 and here P square, you have P square, this is P times P, so multiple of P. And if you are getting P cube, if P cube by P cube, then this should be 1. Okay, since Qi is the order of intersection of two P groups, So Qi, the order of the Qi must be some p power r, and p power r is a divisor of p power alpha. That's why there is a possibility that sum of the pr should be 1. Or each term after dividing, because this is pr1, either r1 is equal to alpha or r1 is less than alpha. If p power r1, say if I am discussing p power alpha 1, alpha by q1, you know, q I is in fact order of h in ai k ai inverse, right? So if q1 is equal to p power alpha by p power r, you know, r is less or equal to alpha, r is less or equal to alpha. So if r is less than alpha, then this must be equal to q1 is equal to p power alpha minus r1. But if r is equal to alpha, then q1 must be 1. That's why I am writing. Since Qi is for I values from 1, 2, 3 to r are the orders of P group, so that each term on the right side must be either multiple of P or equal to 1. Right? Okay. But this implies that now if each term on right hand side is a multiple of P, so should left hand side. Now, being equal to n, if each term on the right side is equal to is a multiple of P, so should the left hand side. But P and M are relatively prime, M and P are relatively prime, so there must be at least one Qi for which Qi is equal to P, Qi is equal to P power alpha. Thus there must be, this is say number 2, thus there must be some Qi for which Qi is equal to P power alpha. So without any loss, assume Q1 is equal to P power alpha. Right. You must have such a term on the right side, because if you are writing this 1 plus P times some integers is equal to M, then of course P is not dividing the right side, because P is dividing this term, but P is not dividing 1, that's why P is not dividing M. So there is this is a balance equation. So there must be some term for which Qi should be equal to P power alpha. So without any loss, without any hesitation, you may assume that this is equal to Q1. So say Q1 is equal to P power alpha. What does it mean? This means that this implies order of H intersection A1 K A1 inverse is equal to P power alpha, which is equal to order of H as well. Okay, and you know that this is a subgroup of H, and if the order of a subgroup and the order of group both are same, then in fact the subgroup is coinciding with that group. But H intersection A1K A1 inverse is a subgroup of H. So this implies H intersection A1K A1 inverse is equal to H. right? Okay, this is a very simple calculation you can see with the help of sets. Since this is a subset of H and the order of this is equal to order of H, that's why both are coinciding, so both are same. You know that if A is a subset of B with the order of A is equal to order of B, then you have only one choice, that is A is equal to B. You have only one choice, that is A is equal to B. I am using the fact. If A is a subset of B with order of A is equal to order of B, then you have only one choice, that A is equal to B. Similarly, since this is a subgroup of H and its order is equal to order of H, so that's why this must be equal to H. Okay, now again, that is H intersection A1K A1 inverse is equal to H. Okay, now if A intersection B is equal to A, what does it mean? If A intersection B is equal to A, look, this is A and A intersection B is equal to this one, A intersection B, this is your B and this is your A. That's why now A intersection B is B. Okay, so here B is the bigger one and A is the smaller one, because intersection is a smaller set. Now look at here, A intersection B is A. Okay, so if A intersection B is equal to A, then A is a subset of B. So here you see that A intersection B is equal to A, so this implies that AH is a subset of A1K A1 inverse. But again, using the same logic, order of H A1K A1 inverse, you know, this is equal to order of K, which is P power alpha, which is equal to order of H. What does it mean? If H is a subset of A1K A1 inverse and both have the same order, then of course both are coinciding, right? So this implies, H is equal to A1 K A1 inverse, where A1 of course belong to G. So what does it mean? This means that H and K are conjugate to each other. This means that H and K are conjugate to each other. Hence, this implies that H and K are conjugate to each other. Okay, this completes the proof. It's a simple proof. You just consider the double coset representation and then you take two subgroups, two Sylow P subgroups. Of course, their order should be same, that is P power alpha. Then write the Lagrange theorem and divide P power alpha. On the left side you will get the index, which is M, and on the right side you will see that each term is in fact being in numerator you have P power alpha, but in denominator you have some QIs, which are in fact the order of intersection of two P groups. So that's why they are their orders are in fact some power of P. So on the right side, either you are getting some numbers multiple of P, or in each term R is equal to 1. Since the left side is not divisible by P, so because you must have sum of the Qi which is equal to P power alpha, so because on the right side you have 1. Say Q1 is equal to P power alpha, that is A1 K A1 inverse is equal to P power, and the rest of the condition are simply by using the idea that if A is a subset of B, then of course their order, if order are same, then A is equal to B. We are doing nothing, so it's a very simple and easiest proof for Sylow second theorem. If you can understand the idea of double coset representation, then this proof is so easy. Now we have few of its consequences, corollaries. The first corollary is a finite group G has a unique Sylow P subgroup if and only if it is normal. So simple corollary. A finite group G has a unique Sylow P subgroup H, has a Sylow P subgroup H, say if and only if H is normal in G, H is normal in G. Okay, yes, you have seen this thing in our previous example. You know, in S3, the order of S3 is equal to 6, which is 2, 3, and by Sylow first theorem, there is a Sylow P subgroup, Sylow 3 subgroup of order 3. So you know this S3 has only one subgroup H, which is A square. This is the, and this group, you know, its order of H is equal to 3, and you know index of H in S3, which is equal to order of S3 by order of H, which is equal to 2. And you know that every group of index 2 is normal. We have learnt in our previous classes in group 3.1 that if you have a subgroup of index 2, then that subgroup is in fact a normal. Also, it is well known that this is the only normal subgroup in S3. Now you can see this result. Since this is normal in S3 and this is the only Sylow P subgroup in S3, right? Yes, we have seen that. This is the only subgroup of order 3 in S3, and also this is the Sylow P subgroup in S3, the Sylow 3 subgroup in S3. That's why you have this result. Okay, so you have G as a finite subgroup and H is a Sylow P subgroup. Now, if H is normal in G, if and only if H is the unique Sylow P subgroup in G. Now, let's prove this. Proof is so easy. We can easily prove this. Suppose H is a Sylow P subgroup in a group G, then by, you know, by Sylow second theorem, you know, by Sylow second theorem, then by Sylow second theorem, A inverse. You know, this is a group subgroup conjugate to H. For A belong to G is also a Sylow P subgroup of G, hence H must be equal to AH A inverse. This implies AH is equal to HA for A belong to G. So this implies H is normal in G. So one thing is very much clear. If H is a Sylow P subgroup in G, then by Sylow's second theorem, you know that any subgroup conjugate to H is also a Sylow P subgroup. So since AH A inverse is conjugate to H, clearly there is no problem to prove that AH A inverse is conjugate to H. So AH A inverse is also Sylow P subgroup. So that's why AH is equal to H by the supposition. If you suppose that it has a unique Sylow P subgroup, this is supposition. First, assume that H is the only Sylow P subgroup in G. Okay, we should write first before proving this result. First, you should assume that H is the only Sylow P subgroup in G, and since this is also a Sylow P subgroup, so this must be equal to H as well, right? This is by supposition. Thus, AH is equal to HA. This implies that H is normal in G. And conversely, suppose that H is normal in G, and you have to show that H is the only Sylow P subgroup in G. Conversely, assume H is normal in G, then AH must be equal to HA for A belong to G. So this implies H must be equal to H AH A inverse for A belong to G. And you know that order of AH A inverse, order of AH A inverse is equal to order of H. Since order of AH A inverse is equal to order of H, so that all Sylow P subgroups using Sylow's second theorem, because are conjugate to each other, are in fact of the form AH A inverse by Sylow second theorem. You know, by Sylow's second theorem, any two Sylow P subgroups are conjugate to each other. Suppose you have AH as a Sylow P subgroup, and I want to show that Sylow P subgroup is unique, and it is very much clear that any other Sylow P subgroup must be of the type AH A inverse. Hence, this AH inverse, the order of AH inverse is equal to order of H. So, because both will coincide, right? Hence, H is the only Sylow P subgroup of G. Okay, we can write this formally as well. If you are not getting the proof in easy words, then I can write this again, like okay, see, conversely, assume let H be a Sylow P subgroup in G. Okay, I need to show that H is the only Sylow P subgroup. Then by Sylow second theorem, A inverse is also a Sylow P subgroup in G, since H and A inverse are conjugate to each other, right? Okay, this is now simple and straightforward. Suppose H be a subgroup, Sylow P subgroup in G, then by Sylow second theorem, A inverse is also a Sylow P subgroup in G. You know that AH and AH inverse are conjugate to each other, and you know that any Sylow 2 subgroups, P subgroup in G, are in fact conjugate to each other. But order of H is equal to order of AH inverse. This is the simple information. You know that if two subgroups are conjugate to each other, then in fact they are isomorphic to each other. If they are isomorphic to each other, then their order are same. Okay. Now see, if the order of these two subgroups are same, then of course both sets are equal. So this implies AH is equal to AH A inverse. This means that H is the only Sylow P subgroup. This means that H is the only Sylow P subgroup in G. Right. This means that H is the only Sylow P subgroup in G. So I have another corollary which is also very much popular and so easy. Okay, next corollary is a Sylow P subgroup of finite group of a finite group G is the only Sylow P subgroup of its normalizer. Okay. A Sylow P subgroup of a finite group G is the only Sylow P subgroup of its normalizer. Mean to say that if H is a Sylow P subgroup in G and you find its normalizer, this is in fact normalizer, that is normalizer of this is normalizer of H in G, and you know that H is a subset of in normalizer, and also this is normal in normalizer as well, there is no problem. Then H is the only Sylow P in its means that its normalizer cannot have other Sylow P subgroup other than G. Say this is the case. Okay, you have H. I want to tell you that Say this is your G, and this one is H, and this one is its normalizer, say N. You know, a normalizer is N H in G. We like to write capital N, capital N. So H, if H is a Sylow P subgroup in G, then H is the only subgroup of its normalizer. Mean that its normalizer cannot have three Sylow P subgroups. Like you cannot have shape of the type H1, H, H2. Okay, what does it mean that H was a Sylow P subgroup of G and H is contained its normalizer, and this normalizer had further three Sylow P subgroups H1, H2, H. Now this is not the case. We are not saying that. We are saying that if H is a Sylow P subgroup in G, this is your G, this is your G. A Sylow P subgroup of a finite group G is the only Sylow P subgroup of its normalizer. If H is Sylow P in G, then H is the unique, H is a unique Sylow P subgroup of the normalizer. Mean normalizer can never have any other Sylow P subgroup other than H. This result says that. And if I have G, I have H, its normalizer, and normalizer is dividing in three Sylow P subgroup, no, this is false in fact. This is not the case in fact. This one is the diagram corresponding to this result. So let's prove this theorem. First we will see with the help of examples. Okay. So one simple idea is if I take S3, you know S3 is E, A square B, AB, A square B, and you know H1 is equal to EB, and from here if I find normalizer of H1 in G, this would be equal to H1. You know normalizer is a subgroup. Normalizer is a subgroup. So S3 has only subgroups of order 2 and order 6. So if the normalizer of this H1 is S3, you know that S3 has three Sylow P subgroups. So you have a contradiction against the fact. That's why normalizer of H1 in G should be equal to H1. If normalizer of H1 in G is S3, and S3 has three Sylow P subgroups, Sylow 2 subgroups. So this would be against the result. That's why I can write directly that the normalizer of H1 in G is in fact H1 itself. Because normalizer is a subgroup, so either it should be H1 itself or it should be S3, because the order of a subgroup is a divisor of the order of group. So normalizer can never be a subgroup of order 4 because 4 does not divide 6. So that's why there are two possibilities. Either it is H1 or it is S3. So it should be H1, right? And also this is not equal to E because in that case H1 would not be Sylow P in its normalizer. So that's why I conclude that this is H1. So let's check. How you find normalizer? Normalizer is normalizer of H1 in G is equal to G belong to G such that G H1 is equal to H1 G. This is the condition. I need to find the normalizer of H1 in G, those elements of G which permute with all elements of H1, right? So we want to see, can you find this normalizer? So let's say H1 is equal to EB. So here EH1 is equal to H1E. So this implies E belong to H1. Now, you know, similarly BH1 is equal to H1B. This implies B belong to H1. Now AH1, this is AB, and H1A, this is A, BA, But you know what is BA? BA is A square B. So you see AH is not equal to HA. So this implies A does not belong to, this is normalizer of H1 in G. This is normalizer of H1 in G. This does not belong to normalizer of H1 in G. So this implies A square does not belong to normalizer of H1 in G. This implies AB does not belong to normalizer of H in G. How can I write directly? Since normalizer is a subgroup, so if A is not an element of H1, how could A square? Because A square is in fact AA. How could A be? Because B is in normalizer and A is not normalizer, so AB is not. That's why you will see that A square B is not an element of the normalizer. So that's why you have only two elements. This implies normalizer of H1 in G is equal to AB, which is in fact H1. Similarly, you can find for other H2, H3, which is E, A, B and E, A square B, you will see that their normalizer are in fact itself, because they are containing Sylow P subgroup H1 and not any other. So, however, if you are taking K, E, A square, this one is, then normalizer of K in S3 could be S3, because S3 contains only one Sylow 3 subgroup, which is K itself. That's why we have no problem here. Here it could be S3, and I think it is S3. You work for this, find the normalizer of K in S3, because AB is equal to BA square. From here A would be the element of the normalizer. So in this case, normalizer of K is S3 is equal to S3, and this is acceptable because S3 has only one Sylow 3 subgroup. So that's why there is no other Sylow 3 subgroup. So theorem is satisfied, right? So let's have its proof. Okay. So proof is let H be a Sylow P subgroup of a group G. Let N, normalizer of H in G is equal to N, say, then N is the subset of H is a subset of N. You know that every element of H is in its normalizer. There is no problem, because at least these elements are permuting with H. So that's why this is very trivial. And since H is a, remember, this is your H, this is your normalizer, and if H is a Sylow P subgroup in G, then H must be in every subgroup of G which contains N, which contains H. I am writing, I can write this. If H is a Sylow P in G, then H must be Sylow P in every subgroup K of G which contains H. Now remember this thing. If H is a Sylow P in G, this is your G. If H is Sylow P in G and N is any other subgroup which contains H, then H must be Sylow P in N as well, because H is a subgroup of N. Here you can write H is a subgroup of N. H is a subgroup of N. Okay, see how I can work roughly. Okay, order of P power alpha, say order of H is equal to P power alpha, divide order of G, and order of H, which is P power alpha, divide order of N. If P power alpha 1 plus 1 divide order of N, and you know the order of N divide order of G, so that's why P power alpha 1 plus 1 will divide order of G, which would be a contradiction against the fact that H was a Sylow P subgroup. So if P power alpha plus 1 divide order of N, then P power alpha plus 1 would divide order of G, since order of N divide order of G, which is a contradiction, which would be a contradiction. Hence P power alpha plus 1 would not divide order of N. It's a very simple consequence. Suppose the order of H is P power alpha, which is dividing the order of G. You know that if H is a Sylow P subgroup, then P power alpha plus 1 does not divide order of G. Suppose P power alpha, yeah, it is clear, because H is a subgroup of N, which is N is the normalizer. So P power alpha dividing order of N. Now if P power alpha plus 1 divides order of N, then of course P power alpha plus 1 must divide order of G, since N divide order of G, and transitivity is satisfied in divisibility. If A divide B and B divide C, then A divide C. That's why P power alpha plus 1 would divide order of G, which would be a contradiction. Hence P power alpha plus 1 does not divide order of N. That's why H must be a Sylow P subgroup in N. So I have given the proof of this small corollary, that if H is a Sylow P subgroup in G, then H must be a Sylow P subgroup in every subgroup which is squeezing between H and the full group. Okay, so you can understand with the help of this diagram. Okay, so since then H is a subgroup of N, also you know that every subgroup is normal in its normalizer. Since H is normal in normalizer, this is very much clear. Those elements of G, what is normalizer? Those elements of G for which GH is equal to HG. This is true. This condition is true. This is the definition of the normalizer. Those elements of G for which GH is equal to HG. If this is happening in N, this is happening, in fact, you are saying that GH is equal for all G belong to N. This one, you are saying that GH is equal to HG for all G belong to N. This was the definition of the normalizer. That's why you can say that H is normal in N. Since H is normal in N, so by the last corollary, H is the unique Sylow P subgroup in N. Hence, H is the unique Sylow P subgroup in N. Now this result is very much clear. I have elaborated with the help of examples and with the help of this remark as well. You can better understand that if H is a Sylow P subgroup in a group G, then H is the unique Sylow P in its normalizer. Okay, this is true because H is always normal in its normalizer, and secondly that if H is a Sylow P in G, then H must be Sylow P in every subgroup of G which is squeezing between H and the full group G itself. This completes the proof, and okay, thank you. In the next lecture we will start Sylow third theorem, its proof and few of its consequences. Thank you very much. Allah Hafiz.